In this question, we have a 55 kilogram astronaut who weighs 180 newtons on a distant planet, and they are pondering whether they can leap over a 3.5 meter wide chasm without falling in. If the astronaut leaps at a 15-degree angle, what initial speed do they need to clear the chasm? Now, the first thing I want you to recognize is that when the astronaut jumps, they will be in projectile motion. And we know for an object that's moving with projectile motion, there is an x component and a y component to their motion. The x component is uniform motion, so there's no acceleration, and we can use the uniform motion equation, which says that Vx is equal to delta x divided by delta t. Now looking at the y component is free fall motion. That means we can use our kinematic equations. But the most important thing that you have to remember is that the acceleration in the y component is equal to negative g. And that's because the acceleration is due to the force of gravity pushing down on the person. And now we know on Earth, the acceleration would be negative 9.8 meters per second squared. And that's because the acceleration is equal to negative g, and g is equal to 9.8 meters per second squared. But in this question, we are told the person is on a distant planet. That means we don't know the value of g. But we can use forces to find g. We were told that the astronaut's weight is 180 newtons, and we know weight is equal to mg. If we rearrange this equation, we can see that the acceleration due to gravity is equal to the astronaut's weight divided by their mass. And so we can plug in those values, and what we find is that g is equal to 3.27 meters per second squared. And now we can use the a is equal to negative g equation to solve for the acceleration due to gravity on this distant planet. And we find that their acceleration is equal to negative 3.27 meters per second squared. Now that we know the acceleration, let's start working on the projectile motion part of this question. I will start by writing what was given. And remember, we have an x component and a y component. Starting with the x component, we know that delta x is equal to 3.5 meters because that's how far the astronaut has to jump. And now we also know that Vx, the velocity in the x component, is equal to v cos theta. And if you don't know where I got that from, remember, because our velocity vector is at an angle, we can break it up into an x and y component. And if we use vector addition to add Vx and Vy tip to tail, we form this right-angled triangle. And because we have a right-angled triangle, we can use trigonometry to solve for the sides Vx and Vy. Starting with sine theta, we know the opposite side is Vy and the hypotenuse is V. Rearranging this equation, we see that Vy is equal to V sine theta. Now looking at cos, we know the adjacent side is Vx and the hypotenuse is V. Rearranging this equation, we see that Vx is equal to V cos theta. Now let's look at our y component. We just learned that Vy is equal to V sine theta. We know the initial position of the astronaut is 0 meters because they start on the ground, and their final position is 0 meters because they land on the ground. And we use forces to solve for the acceleration in the y component, which was negative 3.27 meters per second squared. Now that we know what we were given, let's make a plan. Well, we know we are solving for v. That's the initial speed that the astronaut starts the jump with. And now looking at our x component, we know we can use the uniform motion equation, which says Vx is equal to delta x divided by delta t. I can replace Vx with v cos theta. And you can see in this equation, we have v, which is what we're solving for. But we can't solve for v until we solve for delta t. How do we solve for delta t? Well, we can use our y component. So our plan is to use the y component to solve for delta t, and then plug that value back in to our x component uniform motion equation. So looking at our y component, we can use this kinematic equation to solve for delta t. And I chose this kinematic equation because it does not have Vf. We were not given any information about the astronaut's final velocity, so I want to use a kinematic equation that does not have Vf. And now with this kinematic equation, all I have to do is plug in my values. So the final position was 0 meters, the initial position was 0 meters, VIY, the initial velocity in the y component, can be replaced with v sine theta, and the acceleration in the y component can be replaced with negative 3.27 meters per second squared. And then I will simplify the equation, and I'm left with this. And I hope you can see that delta t is a common factor. So I will pull it out of the equation. And what this equation tells me is that this term has to equal to 0. And now all I need to do is rearrange this equation for delta t. And after we do that, we find that delta t is equal to v times 0.16 seconds squared per meter. And don't worry that we don't have the value of v. We will still take this delta t and plug it into our x component. So remember, the x component is uniform motion. So we can use the Vx is equal to delta x divided by delta t equation. I will replace Vx with v cos theta, and then I can plug in all my values, including the delta t we just solved for. And the next step is to rearrange this equation so that every term with the variable v is on the left-hand side. From there, I will continue to simplify the equation until I can solve for v. And with that, we find that v is equal to 4.83 meters per second. And that is the answer to this question. The astronaut would need an initial speed of 4.83 meters per second in order to clear the chasm. And that's the end of this question, which required you to use forces and kinematics.